faster models. Here's the real question: how does an AI system actually find the right knowledge before it answers? So this is where like the vector database and RAG come in. A language model like can generate text, but the RAG system give the context, and a vector database becomes the memory layer, and embedding turn human meaning into mathematics. Today we are going to break down the architect blueprint for the vector database and RAG, from word to vec and similarity matrix to HNSW and pgvector hardware tuning and production scale RAG architecture. So let's first talk about the architect blueprint for the vector database and RAG. So here is just like it is just not the beginner explanation like for the vector database. This is the architecture view. We are looking at the system design and index algorithm and database optimization. So and all of this support generative AI at the center of the slide. Like you can see the idea clearly: a query node inside a geometry space. Every document, sentence, product, policy, image, or support ticket can be converted into a vector. Then the database asks like one core question: which vectors are the closest to the query, and that distance become meaning. So instead of searching only by the exact keywords, we are searching by the semantic similarities. This is where the foundation of RAG is like begin. So we have the static language model. Like it feels like the enterprise's reality. Static language models are powerful, but they are fail the enterprise's reality. Why? Because they do not automatically know your private documents, and they may not know your latest policies. They may not know today's database changes. They may not know a bit about your company specific acronyms, product names, or the internal workflows. This creates three big problems. First, the knowledge cutoff, and the model may not know what happened after training. Second is hallucination. If the model does not know, it may still generate something that sounds correct. So the third is zero visibility into private enterprises data, and your company's internal knowledge is not magically inside the model. RAG solves this by connecting the models to the external, fresh domain specific context. The model becomes the reasoning engine, the retrieval system becomes the knowledge engine here. So we have the RAG pipeline. So this slide shows you the full RAG pipeline. Like step one is ingestion. Documents are chunked into smaller segments and transformed into dense vector using an embedding model. So step two is like storage. Those vectors are stored with metadata inside a vector database. Design on the high dimension search. And the step three, we have retrieval. When the user asks a question, the query is also converted into a vector and searched against the database using approximate nearest neighbor search. So we have step 4 is generation. The most relevant retrieve context in the injected into the LLM prompt, and the model generate an answer. So this is the basic RAG loop, and ingest, like store, retrieve, generate. But the production RAG is not just about connecting these boxes. This quite depend on the chunking, metadata, embedding and retrieval strategy, re-ranking and governance. So here we have like the translating meaning into mathematics. Now let's understand embedding. This slide shows the famous idea behind word to vec, brother minus man plus woman equals sister. That sounds strange, right, at the first, but it reveals the key idea. Meaning can be represented as the direction and the distance in a mathematical space. Word, sentence, and document are converted into long list of numbers called vectors. In that spaces, similar meaning like appear closer together. So doctor and physician may be close. Refund policies and return policy may be close. Car and automobile may be close, and the model is not matching exact word. This is the comparing meaning as geometry. That is why embedding as the translation layer between human language and machine search. So why the traditional database like fail at the semantic search? So we have like it is the excellent at the exact search. Find raw where the ID equals 42, and find product where the category equals electronics. Find user created after a specific date. That is rational model, but the semantic search asks a different kind of question. If asked like which documents are conceptually closest to this query, a traditional B tree index is not designed for that. If you are trying to compare dense vectors using brute force, you may have to scan every vector one by one. That become impossible at the large scale. So vector database solved this by using approximate nearest neighbor search instead of perfect brute force scanning. They may spatial like index that can find similar vertex quickly. So the trade-off is traditional database are built for exact conditions, where the vector database are like built for similarities, and we have a geometry of similarity matrix. So to search vectors, we need to way to measure like closeliness. This slide shows the three major similarities matrix. First is cosine similarity. Cosine similarity measures the angle between the two vectors. It ignores magnitude and focus on direction. This is extremely common for text embedding because meaning often depends more on direction than length. The second is um, Euclidean distance like or L2. This measures direct physical distance between the 2 points. Lower distance means higher similarity. And the third is dot product. So dot product measures both the directions and magnitude. It is the efficient for com compensation and like work well when the vectors are like normalized. So when someone says like the vector database found similar documents, what really happened is like mathematical comparison. The database measure distance or similarities between the query vectors and stored document vector at the search is basically geometry wearing a hoodie. Let's talk about the engine HNSW. Now we get to the engine behind like fast vector search. So here is like an HNSW stands for the hierarchical navigable small words small worlds. So that sound like complicated, but the idea is elegant. So the imagine a city map. At the top layer you have highways, at the middle layer you have major roads, at the bottom layer you have local streets. HNSW works similarly. It creates multiple graph layer that the upper layer are sparse and the help to search more quickly towards the right region. Then the algorithm drills down into the denser layer to find the nearest vector more precisely. This avoids the brute force scanning, and instead of checking every single vector, HNSW like navigates the graph intelligently. This is why HNS can deliver fast similarity search even the massive scale. So we have one more, which is the vector database landscape. So now let's compare the vector database landscape like Pinecone in a like managed cloud option. It is a strong when you like want zero operations or fully managed vector search. So Weaviate is like useful when you like want the hybrid search combining BM25 and keyword like search with the vector search. Milvus is designed like for the massive scale and distributed enterprises workload, and pgvector is interesting because it brings vector search into Postgres, and that matters because many team already use Postgres. If your application has medium scale RAG requirement, so pgvector lets you keep rational data and vector data together. So the choice depends on your architecture. If you manage infrastructure, Pinecone may fit. If you want hybrid search, Weaviate is strong. And if you need huge distribution workloads, so Milvus is the build for that. And if you are already live inside the Postgres, PG vectors can be the pragmatic choice. So this is no universal best database. There is only the best fit for your scale, team, and constraint. So the parametrics choice, the Postgres plus like PG vector. We have one more, which is the slide focuses on the Postgres with the PG vectors. The key idea is co-location. So your relation data and the vector data live together here. So instead of maintain a separate vector database, syncing data between system and handling extra latency, you can run vector search inside Postgres. That example query shows the power first and apply a normal rational filter. For example, category equals electronics, then order result by vector similarity. That means among electronic products, find the one most semantically similar to this query. This is the power of a medium size RAG application. If you have around like 100,000 documents or a controlled internal knowledge base, Postgres plus PG vectors can be the practical and efficient. It is reduces the operational overhead. It keeps ACID compliance, and it allows developers to use familiar SQL. Sometimes the best architecture is not the fanciest architecture. It is one of your team can actually maintain. Let's optimize the ingestion. So the software bottleneck, Now we are moving into the performance, like where the vector database are not only about query speed, ingestion speed matters too. If you are building a RAG system, you may need to insert thousands of or the millions of embeddings. The slide shows how software level optimizations can be dramatically affect throughput. The comparison between the pgvector version shows a major speed up during the concurrent inserts. Why? Because the building an HSW index requires distance calculation. If the software reduces unnecessary calculation, ingestion becomes much faster. This matters in production because data is not static. Document change like the policies update, logs arrive, new tickets are created, product data changes. A real rack system needs continuous ingestion. So optimization is not just nice to have, it decided whether your rack system can stay fresh. So hardware reality, so vector size versus Postgres pages, like now let's talk about the hardware reality. Vectors are not only free, like a1 to a dimension vector is like relatively small, but 1536 dimension vectors can be consume much more memory and may even take an entire Postgres memory page. That means more disk read, more CPU pressure, and more latency. This is where the people often underestimate vector search. They think like only about embedding conceptually, but in production, embeddings become physical data. They sit on disk and they move through memory, they hit CPU caches, they affect throughput. The slide also shows that the hardware solution, graviton optimization for high dimension vectors query processing, can be become heavily CPU bound. Better floating point performance can be reduced, like query latency significantly. So the vector database architecture is not only math, it is also hardware engineering. That shapes for the vectors affect the shape of the infrastructure build. So let's scale the grid production maintenance. So at the scale, like vector database need maintenance strategy. First, shredding, hash based like shredding distributed vectors evenly, and but it may like force scattered gather queries across shared partition based like cluster can reduce latency by keep related vectors together. Second, eventual consistency, like a vector search is already approximate, so asynchronous replication can work well. A slightly stale read replica may still return strong semantic matches. The third is background compassion, which is HNSW often uses soft deletion to maintain the graph connectivity. But if uh, dead nodes pile up, query performance can delay. So the background um, compassion is like mandatory. This is the production side of vector database that tutorial often skip. It is not just store, embedding, and search. It is shred, replicate, complicate, monitor, and tune. Vector search at the scale behave like infrastructure, not magic. So we have the generative AI tech stack. So at the bottom, at the bottom, like we have raw enterprises data, documents, database logs, email tickets, policies, and internal knowledge. Next, the transition layer, like the embedded models convert that unstructured data into high dimension vectors. Then comes the navigation grid, the vectors database using system like PG vectors and HNSW executed fast proximity search. Finally, the application interface, the LLM receives the retrieve context and generates the ground answer. This is the real RAG architecture. The LLM is not alone. It is sitting on the top of the full knowledge pipeline, and the raw data becomes embedding, and the embedding becomes searchable vectors. So here the vectors like become the retrieval context, and retrieval context become the grounded generation. This is why RAG is such a major shift. It combines semantic mathematics, scalable indexing, and database engineering and generative AI. So we are here like for the final closing, which is like the vector database are not just the storage for the embedding, they are the memory and navigate layer for the modern AI systems. Embedding translate meaning into numbers. Similarly, metrics compare that meanings, and the indexes like HNSW make search fast. Tool like PG vector brings vector search into existing database, and systems like the RAG connected all four of this like language model, and so the AI can answer with retrieval relevant and the retrieved context. The future of AI is not just bigger model, it is the better retrieval, better memory, and the better architecture, because the LLM writes the answer, but the vector database help it to find what it should know. So thank you so much for everyone to be here on this video. If you like the video, like just punch the subscribe button, and I hope you will like this video, and I will like produce more on RAG stuff. And definitely, like, I mean, if you have any topic, so just give me in the comment below. So thank you for everyone to be here.
This is Abhishek Yadav signing off from Curio Mind Show. Stay curious. Until next time, keep observing, keep interacting, and keep discovering. If you enjoyed this video, make sure to hit the like button, subscribe to the channel, and don't forget to press the bell icon so you never miss an update. Thank you for watching.